In this video, we are gonna learn a technique that would allow us to optimize the propagation delay in a combinational circuit. This will be done by sizing properly the transistors and by creating chains of the adequate length. We will start giving a general overview of the problem.
During these slides, we use a very specific notation. This notation is different from the one in class. Cint represents the output capacitance of a logic gate, while Cgin is the input capacitance. When we put an inverter with a number on the left, it represents a generic gate with a size of the specified size. With this size, we can obtain the input capacity as they are directly proportional. Now that the notation has been presented, we can proceed to explain the problem we want to optimize. It's common that after some combinational circuits we have big loading capacitances, which may come from a long line connected to a gate, internal capacitances, and the capacitances from the transistors themselves. These capacitances generate a rising and declining delay, which makes our circuit slow. This delay can be computed using the following equation, which takes into account these capacitances and the internal resistances. The equation can be rewritten as a function of a base delay and the delay caused by the fan-out capacitances. The fan-out and the base delay can be computed using the formulas from the slide. The concept of the fan-out is normalizing the loading capacitance using as reference the input 1. Therefore, if we compute the fan-out of a gate connected with a replica of itself, the fan-out will be 1. On the other hand, the base delay is used in order to allow comparison between cases without the need to compute the exact result. For simplicity, the assumptions on this slide have been done along all the presentation. Cin is equal to Cout, and Rp is equal to Rn. Using different values would make the concept harder to understand. To illustrate the problem, we will give a brief example. Here we can see three different circuits with the same input and loading capacitance. The first one consists in a single stage and the other two in a two-stage chain with different gate sizes in each stage. Remember that the number near the gate represents the size of the transistors. Cl is also put as a function of the size. You take the real Cl and divide it by the C unit, obtaining a new value which is in a more comfortable unit to make the calculus. In the circuit above, the delay is computed by obtaining the delay of the gate. In the other two, we have to obtain the delay of each gate and then add the delay from the first stage and from the second stage. In a more complete chain, the total delay of the chain is obtained by computing the delay in each stage and then adding all them together.
In this slide, what we show is the equations and the steps used to compute the delay from each step. You can pause the video to review them, but now we are just presenting the idea of the problem. So we will follow to the next slide in order to see the total delays of each structure. Once we have computed all the delays, we can see that all depend from the baseline delay, in this case T sub O. This delay is multiplied by a different value in all the three cases. As it can be seen, the single stage case has a much bigger delay than all the other ones. And what we can also see is that the two-step cases also have different results between them. This means that we have to find not only the optimal number of stages necessary, but also which is the distribution of capacitances that would allow us to minimize the delay from the chain. We will first analyze the optimal distributions of capacitances, and later we will obtain the optimal number of stages necessary. First, we look at the delay caused by one inverter. We can see that it depends on its load and internal capacities. This F means the fan-out, which is the relationship between these two capacities. Let's see how we do it with N inverters. We can see that in an inverter chain, the C load is the C gate of the next inverter. And applying this identity here, Cint is equal to C gate in, we have the following. As we can see, each time J depends on the relationship between the capacities of the J inverter and the next one. Each inverter J has its own delay TPJ, and the sum of all these times is the total delay of the system, in this case TP. We are going to solve these equations in the next slide. We have this expression from the previous slide. In this case, we have n-1 unknowns, from Cg in 2 to Cg in n. To optimize it, we have to do n-1 partial derivatives. The result is the following. This leads us to the next expression. We get a fan-out for each inverters. All these fan-outs are the same value due to the equation in the green square that we found before. So if we simply multiply all the fan-outs, we get the following result. Then we get this capital F value that we are going to use in the next slide. We keep this expression from the previous slide. We can do some simple manipulation to isolate the fan-out. With this expression and the number of stages, we can compute the optimum input capacities of all the transistors in our chain. To calculate the optimum time with a given number of stages, we need to recall these equations that have appeared before. Then we can find that we can write the delay as a sum of 1 plus fan-out and a baseline delay. Then we substitute the fan-out with the uppercase F using the top equation, and then we can proceed to do the summatory. As all the terms in the summatory are constant, we can simply change the summatory from 1 to n to simply multiply by n. Now we can calculate the optimum delay with n stages using the formula. In these slides, we can see a summary of how to calculate the capacities for each step. We first compute capital F by dividing the C load with the CG in. From this capital F and the number of stages, we can compute F, and therefore we can now compute all the capacitances in each stage. And now that we are able to compute all the capacitance distributions, we have to learn how to compute the optimal number of stages. At this point, we know how to get the proper size distribution of a chain of inverters if we know the number of stages, the loading capacitance, and the input capacitance. But is there any number of stages that leads to the minimum delay? If we get the equation from the total delay by adding all the delay from each stage, we can get the following formula. This formula depends on n from the fan-out and the baseline delay. We can derive it as a function of n and equal it to 0. And after some manipulations, we can get to the conclusion that f is equal to the exponent of 1 plus 1 divided by f. This equation cannot be solved analytically, so it has to be solved by using MATLAB or any other tool. We can get the result that f has to be circa 3.6, and from this we can go up to this other expression, substitute the 3.6 and get that the n is the log of 3.6 of the capital F. This will give us decimal value, which has to be rounded off to get the optimal number of stages, which will minimize the total delay of the chain of inverters.
In this slide, we can see an example of the complete methodology to obtain the optimal n. We first compute capital F taking C loading and C G in. Then we do the log base 3.6 of capital F and we find the optimal n. Notice that the result might have decimal values. We need to choose one of the two closest integers. In some cases, we may need to compute the total delay of the chain from the upper closer integer and the lower closer integer, and then see which one gives a better total delay value.
As we have seen in these slides, properly sizing the transistors can let us control the amount of delay chain of gates have. This can be useful, for example, in the distribution of a clock inside a device, as some devices may be more far away from the clock and therefore may have higher capacitance than others closer to them. This difference in the capacitances could lead to different clock delays, making that the whole device is not fully synchronized. Another field of application could be the design of matricinal combinational circuits with high capacitance, which may come from long wires in the chip. Some circuits that could benefit from this technology are memory decoders, multipliers, and the design of buffers.